Hi, I'm Adam, and today I'm talking about AIDS, HIV, and PrEP. First off, acronyms. Why? What do any of them mean? Okay, super quickly. AIDS, Acquired Immunodeficiency Syndrome. Literally, the list of symptoms that show that your immune system isn't working and that you got by an infection and not, say, radiation or something genetic. HIV, Human Immunodeficiency Virus. Literally, the virus that causes AIDS in humans. PrEP, I'll get back to later. I promise it'll make more sense that way. Okay, so what's a virus? It is simply some genetic code in a protein box with just enough extra stuff to hijack a cell and get the cell to make more of it. On its own, it can't do very much. Can't move on its own, can't make energy on its own, can't take stuff in from the outside, can't react, can't reproduce, nothing. By all measures, it isn't really alive, but crucially, because of how little it can do, and therefore how little it needs to exist, it can be tiny. Like, teeny tiny. Like, have you seen this guy? He's called a bacteriophage, and he inspired these guys. These little legs here are literally 1 molecule wide. Like I said, tiny. Keep that in mind, it'll come up a lot. Okay, to make sense of how HIV works and why it's special, I need to tell you more about how a normal virus works. So, time for our first bit of context. Okay, a virus. On its outside, it'll have all these sticky outy bits. And these sticky outy bits have a very specific shape. They connect to one, sometimes two, specific sticky outy bits on your cells. If the cell doesn't have that specific sticky outy bit, then it can't connect to it and it just bounces off. So a virus gets inside you, however, and it connects its sticky outy bits to your cell's corresponding sticky outy bits. Okay, on the cell it's called a glycoprotein. Doesn't matter. Because it's so tiny, the act of connecting to something changes its shape. And that shape change lets it insert its genetic code into your cell. Remember, it's not alive, so think less syringe and plunger and more two bubbles merging together. Once the genetic code is inside, the other stuff the virus needs to hijack the cell gets to work. This differs depending on the types of virus, and there's tons of different flavors. To make life simple, let's just talk about HIV's way of doing it. HIV's genetic code is RNA, and yours is DNA. So to get its code into yours, it needs to turn the RNA into DNA. Biologists will know that turning DNA into RNA is called transcription. Well, the reverse is called reverse transcription. And the enzyme that does that is reverse transcriptase. Thing A's just means the enzyme that does thing in biologist ease. The virus's DNA now needs to get into the cell's DNA. This is called integration, and it uses integrase. Shocking, I know. Once the virus's DNA is in the cell will just assume the DNA is part of its own and follow the code. Oh, make more of the reverse transcriptase and integrase. Sure, why not? Make more of this protein. Okay. Quick aside, the protein making is done using protease. Just remember that name, it'll come up later. Make more of this specific RNA section. Fine. Once the protein has put itself together, send it out. Will do. And so the cell makes more of the virus and sends it out into the rest of the body. Okay, that was dry. I'll try and make the rest of this a little more fun. Okay, now remember how the bubbles merged earlier and the virus has specific sticky outy bits? They're still there, and they're recognizably different from your normal cells. Think zombie movie. You've got a cell that's been infected and it's about to turn and infect everyone if you don't stop it quickly, and everyone can see that they're infected and nobody knows what to do, and then natural killer cell comes along and talks to the infected cell, and natural killer cell is the stone cold cop who's 10 days from retirement and talks to the infected cell like, you know what you have to do, and triggers apoptosis in the infected cell. Apoptosis is programmed cell suicide, which I guess is most comparable to honorable seppuku. Okay, so this is a samurai zombie movie now. Run with it. So once the cell has committed suicide, it breaks down into smaller pieces, and, crucially, the viral bits are still there. So in come the forensic scientists, and they're called dendritic cells. They take the parts they find back to the centers of the immune system, called lymph nodes, and there they show this new bit of virus, it's called an antigen, to the much more powerful immune cells. And eventually it'll find a team of 3 cells, T helper, T killer, and B, who are born with corresponding receptors to this antigen. And they'll be like, we've been training for this our entire lives, and spring into action. And they form an army, and it's called in to fight the samurai zombies. First, there's B cells, who fire antibodies into the world. They're powerful little chemical bullets that stick only to the viral antigens and disable floating viruses, or that stick to the antigens on infected cells with a note that says, if you can read this, you've been infected and you know what you must do. And the note hands them their sword. There's T killer cell that heads out into infected areas only and hunts down and kills every infected cell systematically, ruthlessly, and with way more efficiency than the natural killer cells ever did. Then there's T helper cells. They produce chemical signals called cytokines. When T killer and B cells receive the cytokines, they activate and get to work. When they stop receiving them, they stand down. So in this case, they're like the commanders giving orders to the army of T killers and B cells. They're the ones that switch the body from passively watching out for invaders to fighting off one specific infection with the full force of the body. But the virus isn't idle during this. It'll keep mutating to try and avoid detection by the army, sending out its horde of ever-changing zombie ninjas to try and avoid the army. But the army's adaptable too, and the arms race is on. Can the army adapt fast enough to kill the zombies before all of the body is infected? Find out in the thrilling conclusion of Viral Infection. Cue the theme music. Okay, I might have gotten a bit carried away there. Okay, back to being professional now. So, HIV. HIV can only bind to the CD4 receptors. And we call cells that have CD4 receptors CD4 plus cells. Or we call them T helper cells, the commanders from the weird anime I accidentally just wrote. As you can imagine, the more of them get infected, the fewer commands they can give out, the fewer cytokines. And so the harder it is for your body to switch its immune system to fight a specific infection. This is why in HIV infections they measure your CD4 count. The higher it is, the more active commanders you've got, the more your body can fight off infections. The other big problem with HIV is it's even more mutation happy than normal viruses, and it's even tinier than normal viruses. Antibodies just don't seem to slow it down at all, and even when they do, it just changes shape to dodge them. So you can understand why HIV can run circles around an immune system if we don't treat it. Untreated, HIV goes through 3 phases in humans. Phase 1 is the acute phase. You've just got HIV, and your body is trying to fight it off. It attacks and kills some CD4 cells, but ultimately the fight isn't one your body can win. The virus mutates away, the body stands down its immune response, and everything just sort of quietens down. In some people, this all happens without them ever knowing. In others, they go through what feels like a bad bout of the flu. We can detect the virus using PCR and the antibodies using much faster tests in this stage. Then it goes on to phase 2, the chronic phase. It's not 100% obvious why your body stops trying to fight the virus while it's still there, or why the virus stops killing CD4 cells so fast, but we know it happens. In this stage, the virus slowly replicates and slowly kills CD4 cells. It can last years. We measure the progress of the disease in this phase by the CD4 count and the viral load. The metaphor I was taught was that the CD4 count is the miles remaining, and the viral load is the speedometer. The higher the viral load, the quicker the CD4 count goes down. When your CD4 gets too low, that's when your body can't fight off any infections anymore, and you hit stage 3, AIDS. Infections that were once easy to fend off can now run rampant. The tuberculosis your body had managed to force into a granule in your lungs can now kill you. The herpes virus you had dealt with ages ago can now progress all the way to Kaposi's sarcoma. We actually only learned of HIV's existence because there was an outbreak of this incredibly rare type of cancer. This newspaper was considered the start of the AIDS epidemic in the West. And here's where it gets dark. See, in a perfect world, as soon as a new epidemic appears, humanity would spring to its own defense and try and fight it off, right? But humanity is divided into nations, and nations have leaders. And if the leader of a nation has tried to label himself as a moral crusader, and the people the epidemic affects the most are the people he's crusading against, then you're not going to get a very fast response. Or any response. Or maybe his spokesman will laugh when an entire generation of those people are dying. And the epidemic will run rampant because it's just not politically useful to spend money saving people's lives. Personally, I find this decision, this choice that he made and that others continue to make, to be unforgivable. And I hope that justice finds everyone who made it. But anyway, moving on. What we can do, there's hope. So the virus's size and simplicity gives it an edge in dodging your body's immune system. But it also gives us an edge in fighting it. If there's only so much it can do, there's only so much we have to fight before we can stop it from doing anything at all. The virus comes in, turns its RNA into DNA, integrates its DNA into ours, and makes more of itself. We can block its entry with entry inhibitors such as Maraviroc. We can block its reverse transcription in 2 different ways, nucleoside reverse transcriptase inhibitors, which are basically letters in the DNA that aren't in joined up handwriting, and they end the sequence before it can make any sense. And non-nucleoside reverse transcriptase inhibitors, drugs that attack the enzyme literally any other way, such as tenofovir and etravirine, respectively. We can block the viral DNA from getting integrated into the cell DNA using integrase inhibitors such as raltegravir. We can block more of the viral proteins from being made with protease inhibitors such as darunavir. In the early days, we only had the one drug to treat HIV. It was called AZT. It was really toxic. And because HIV is so good at mutating, it would only last for a while before the virus would just mutate around it and get back to killing you. Then, in the 1990s, we had enough different types of treatment that we realized we could avoid the virus mutating around the treatment by treating patients with multiple different classes of treatment at the same time. A virus will mutate around one mistake every 250 bases, in its genetic code. This is the fastest of any known biological entity. It has a genetic code 9,200 bases long. So every time it replicates itself once, it'll have made about 40 mistakes. The odds of those 40 mistakes causing it to mutate around any one treatment are really slim. The odds of those 40 mistakes causing it to mutate around one treatment and then another are really slim squared. One treatment, then another, then a third, really slim cubed, and so on. And only one drug needs to work to completely stop the virus from replicating in a cell. Current guidelines are to have 3 drugs of at least 2 different classes at any one time. It's called combination therapy or highly active antiretroviral therapy, HAART. These pretty much guarantee that the viruses can't make more of themselves. So that's that, right? It's cured. Well, not quite. We can stop the virus making more of itself, and your body will slowly flush out all of the floating viruses inside you until there aren't any left. This is called an undetectable viral load. Once that's happened, you can't transmit the virus anymore, because there's nothing to transmit. And generally speaking, as long as you keep up your treatment, you're indistinguishable from someone who was never infected. The problem is, some of the viruses could have gotten into a long-lasting cell. If you stop taking your treatment, the long-lasting cell will just start making more of itself again, and you have to start over from square one. So, it's a manageable disease like diabetes or asthma, but it's not a curable disease. Yet, anyway. But wait, what if we stop the virus from ever getting into one of your long-lasting cells? Then, once your short-lived cells are all gone, and you've got no more virus floating around, and no more viral DNA, isn't that a cure? Yes, but also technically no. This does work, and it's called prophylaxis, because technically you're stopping the disease before it happens, and not after it happens, which is a cure. Like I said, yes, but not technically. Prophylaxis comes in two flavors right now, PEP and PrEP, post and pre-exposure prophylaxis. Remember how I promised it would make more sense if I introduced this later? In post-exposure prophylaxis, as soon as you've been exposed to the virus, 72 hours at most, you rush to the doctor and take your first set of pills. You go for 30 days, and then by the end of it, the virus has all been flushed out, the cells that have been exposed to the virus have all been flushed, and you got there in time. In pre-exposure prophylaxis, you take one pill every day. It contains 2 different antiretrovirals, so the virus can't mutate around it in time, and it's 99+% effective at preventing the virus from taking hold if it ever gets inside you. There are some side effects, and you have to see the doctor every few months for checkups if you start it, but frankly, some minor stomach problems and headaches, and even then only if you're unlucky, those are a fair price to pay for a shield against HIV. Okay, so what did we learn today? We learned what a virus is and how it replicates. We learned how viral infections typically progress. We learned how HIV infects cells, which cells it infects, how it binds to them, and how the infection progresses. We learned how antiretrovirals work. We learned that undetectable means untransmittable. We learned what combination therapy is and why it's been a vital step in fighting the AIDS crisis. And we learned what PEP and PrEP are and why they are the next important step in fighting the spread of HIV. Thank you so much for listening, and good luck out there.